one of the things that we notice rather quickly about the planets is that they have magnetic fields. Earth is famous for having a magnetic field. Compasses point north. They interact with the Earth's magnetic field. In fact, Earth acts like it has a great big magnet inside of itself here. So it acts like there's a great big magnet inside of the planet, and that magnet is what's interacting. So what's happening is that we've got this magnetic pole, the north magnetic pole. Now here's the interesting thing is we know that north end of magnets or repel each other, south ends repel each other. Okay, so north and south attract. So that means if the north end of a magnet is attracted towards the Earth's magnetic north pole, that's magnetically really a south pole. So really the Earth's geomagnetic north pole is a magnetic south pole. And Earth's geomagnetic south pole is really magnetically a north pole. So that's an interesting sort of thing. But the other interesting thing is the alignment of the north and south magnetic poles, the geomagnetic poles, are really not exactly lined up with the rotational axis of Earth. They're shifted a little bit. They're shifted a little bit in terms of being tilted respect. They're also shifted a little bit in it acts like the magnet inside the Earth is slightly off center, and so that impacts things too. Now, the way magnetic fields work, if you had something with a bunch of magnetic fields and you dumped a bunch of iron filings around, it would make kind of a shape here that actually is very much like the shape of the Earth's magnetic field. And so what you would do is, to understand how magnetic fields work on planets, you'd try to replicate this in a laboratory. Now, one interesting thing is we know that the core of the Earth is iron and nickel, and so you might think, well, oh, it might just be a big magnetized thing. Well, not really, because it turns out if you heat a permanent magnet, like an iron magnet, and you heat it enough, there's something called the Curie temperature. If you get above the Curie temperature, then the little magnetic domains become randomized, and just thermal motion randomizes everything, and you destroy the magnetic field. So a magnet becomes non-magnetic if it's hot enough. Well, it turns out the interior of the Earth is way more than hot enough to destroy any permanent magnetism. So you got to figure out how else do you make magnetic fields other than with a permanent magnet. Well, physicists know that the way you make magnetic fields is with electric current. It's the idea of an electromagnet. And so the idea would be that inside the Earth is a magnetic current of some sort, or a magnetic field making it. Now, why is this important? Because electric currents make magnetic fields, but magnetic fields exert forces on electric currents. That's the whole idea of an electric motor, is that you have electric current in the motor, and a magnetic field produced by magnets there is going to exert a force and torque or twist the turns in the motor, and so that's how you drive an electric motor. You can also use magnetic levitation, magnetically levitate something again with electric current. Any electric fields, rather any electric current. So electric current is just moving electric charges. And what we discover is there are a whole bunch of moving electric charges that are coming to us from the sun. And so as they're coming to us from the sun, they're interacting with the Earth's magnetic field, and they're going around Earth. Now that turns out to be very important, because if the magnetic field were not there, these charged particles would be coming right through and slamming into Earth. That would have several influences on us. First of all, it'd start ablating our atmosphere. It would actually change the character of our atmosphere. Secondly, it would cause these charged particles slam into the atmosphere to cause a cascade of radiation down to the surface of the Earth. And so Earth's magnetic field protects us from that. Now, there are some particles that are caught in the magnetic field, and as they're caught in the Earth's magnetic field, they just move back and forth in the magnetic field, and as the magnetic field bends around, they get bent around, and they do slam into the atmosphere up near the north and south magnetic poles. And so in that case, when they do, they actually do interact with the atmosphere. They're not as energetic as the straight particles from deep space, but they do interact and they create the aurora. Now, you do have particles raining down on you in the aurora, and so it's a bad idea to actually fly an airplane through an auroral display because you're going to be bombarded with radiation if you do that. And so that's generally a bad idea. But the Earth's magnetic field does protect us from radiation. So how do we get that magnetic field? Well, as I said, we need to have some kind of electric current. And one way that happens is deep inside the Earth, we have an iron and nickel core. Now, the thing is that iron-nickel core is so hot, the outer part of it is molten. Now, the inner part is actually squeezed into a solid layer, but the outer part is molten. And so molten core means that it's free to move around. So as Earth rotates, then one of the things we discover is the outer parts of the Earth rotate at a tiny, tiny, tiny different speed than the core of the Earth. That creates a little bit of turbulence in there, a little bit of shear, and you can actually get a little bit of static electricity in there. That little bit of electricity, as the Earth rotates going around, can produce a magnetic field. And then you start getting more turbulence inside the core, more turbulence inside the core, sustained, currents in there, and once again, that reinforces this magnetic field. We call this the dynamo effect. Now, we believe that something like this dynamo effect is what produces all planetary magnetic fields. Even in planets like Jupiter or Saturn, which don't have an iron-nickel core, they have another type of metal in there that is able to be electrically conducting and do the same thing. And so this dynamo effect, even in the sun, plasma, which is charged gases moving around inside the sun, produce a magnetic field. This is your standard way of making magnetic fields. So the liquid conducting region is necessary, but you have to turn it fast enough. So if a planet doesn't rotate very fast, then even if you get electric charge in there, it's not moving very fast, and so there's not much electric current to make an electromagnet. And so you need to have a relatively rapidly rotating core, and you need to have it liquid. Okay, and so that becomes very important. So if you see a magnetic field, that's generally taken as some evidence that you do have a liquid planetary core of some sort. And so that's exactly what's liquid and what is, it has to be a liquid conducting region. So exactly what liquid and what conducting, you got to work that out later. Now, there are a couple of exceptions to this. The planet Mercury actually rotates too slow, according to theory, and yet it does have a weak magnetic field. And so that's a little bit confusing as to why that's the case. But all the rest of them seem to fit with our dynamo model. So Mercury, Mars, and Venus, or the Moon, Mars, and Venus, rather. The Moon and Mars are so small, they are mostly solidified on the inside, and so you're not going to get much of a magnetic field. Venus is like Earth, so it probably has a liquid core, but Venus rotates very slowly, hundreds of days to rotate, instead of like 23 hours and 56 minutes like Earth. And so it rotates very slowly, so not much of a magnetic field. Mercury has a weak magnetic field, and that's weird because we don't expect it to have a magnetic field because it's only slightly larger than the Moon, and it rotates slowly. So it has multiple things going against it, and so something else has to be at work inside of Mercury to generate a magnetic field. One possibility is because it is so close to the sun that interactions with the sun itself is what's giving it the magnetic field. So it might be doing something different to create its magnetic field compared to everything else. Earth, Uranus, and Neptune have magnetic fields that are considered moderate, in strength, and they probably generate magnetic fields in very similar fashions. Uranus and Neptune's magnetic fields are somewhat different than ours, and they're tilted or inclined very heavily with respect to the planet's rotation. It is likely they are produced in a different layer inside those worlds than, for example, the core, which is where Earth's magnetic field is being produced. Uranus and Neptune's magnetic field may be produced in like a mantle for them. And Jupiter and Saturn both have extremely strong magnetic fields. Jupiter, one of the strongest magnetic fields in the solar system, other than near a few sunspots. And so Jupiter and Saturn have these massive magnetic fields because they are massive worlds that rotate very rapidly, and they have very huge conducting regions to make magnetic fields. So this is our basic study of planetary magnetic fields.